Welcome everybody to Physics C Mechanics. I'm Angela Jensvold, and today we're going to continue our review of the conservation of energy. I left you with this for homework yesterday, so let's take a look at it. We talked about energy and systems yesterday. So when you think about this ball swinging down, you can think about it in a couple of different ways. If you say the ball is your system, then you have an external force of the earth doing work. And you would say the work done by the earth is equal to the change in energy of the ball. If you call the ball and earth as your system, like the earth is here, I guess, then you would say there are no external forces because we're ignoring air resistance. And so there is no work done, external work done. So the change in energy is zero. So that means that initial energy is equal to final energy. And if you're including the earth in the ball, then there's gravitational potential energy. Remember, in the first scenario, the red scenario, the ball cannot have gravitational potential energy. You need two objects to store gravitational potential energy. So, but since we're going to use the blue scenario, which is the earth and the ball, then you would start with gravitational potential energy. And then at the bottom, you would have kinetic energy. So V depends on the height at which you release the ball, right? Because this was height initial. Okay, so this is the height, the initial height that you let go of the ball. Okay, so the question is, why is the ball moving slower than expected? Okay, so if V is small, must have been initial height was smaller, right? So the measured velocity is less than the calculated velocity. So how can you account for that? Well, why would the initial height have been smaller than the calculated height? Well, when you calculated the height, you're thinking, okay, this girl's going to let go of the ball at 2 meters. So she's holding the ball, right? But are you perfect at holding a ball at 2 meters above the ground or 2 meters above the lowest point? Probably not. She might have maybe straightened her arms a little bit, right? So maybe she released it from a lower height than you had anticipated. How about that? Those are the kind of experimental uncertainty questions that you'll have to answer on the exam, qualitative in nature. Okay, so today we're going to look at two learning objectives, and here are the main ideas. Remember, it's the same as yesterday. Okay, but honestly, it's so important. Energy conservation is so important. We're spending 2 days on it. It's a huge, it's just very important. So anyway, mechanical energy. If you remember from yesterday, it's the sum of kinetic and potential energies. The work done by a non-conservative force means like a dissipative force like friction, is equal to the change in energy. So a work, try to remember work is a transfer of energy into or out of a system, right? So in the example we just did with that bowling ball, and we had the ball as our system, the earth is transferring energy into the system. Okay, and then I just slipped this in here for a third time to remind you that the work energy theorem can only be used on a point particle, right? Nothing that has the capacity for internal energy. Okay, all right. So yeah, mechanical energy, identify your system before you begin, just like we did with the bowling ball. Use an energy bar chart to organize your thoughts. If this is zero, look at this equation on the right. If this is zero, there's no external work done, then the change in energy is zero, just like we said with the bowling ball. Okay, here's a experimental question for you guys. Give it a shot. Okay, I hope you guys drew a force diagram. Okay. Um, so basically, you have here are the coffee filters. You have the force of the earth on the coffee filters, and then you have the force of the air on the coffee filters, which changes, right? So at first, the force might be kind of small because the speed is small. This is the force of the air on the coffee filters. So terminal speed is the instant when I'm going to draw in red, when the force of the air on the coffee filters is equal to the force of the earth. And if those two forces are equal, the acceleration will be zero, right? When acceleration is zero, the coffee filters reach a constant speed, and that's called terminal velocity. Okay, so we're looking for the condition when the acceleration is zero. And our forces downward is the force of the earth, mg, and upward is cv squared. That's the force of the air. So if you saw, oh, by the way, this corresponds to terminal speed, right? So v terminal squared would equal mg over c. Okay, and then they say plot a linear graph. I got a little head start just so we don't waste time. Plot a linear graph. What would you have to graph? Well, you're trying to get our y variable would be vt squared, and we want slope times the x variable. So the x variable would be the mass. Okay, so you're going to graph v squared, v terminal squared, so it'd be meters squared per second squared, versus mass. And those are all times 10 to the minus 3 kilograms. Okay. All right, now you have to use your graph to find C. Well, look at our variables here. So the slope would be G over C, right? So if we calculate G divided by the slope, we'll get C. So let's get the slope. I hope you're catching on at this point and how to use a graph. You have to find 2 points on the line. You don't use data, okay? So I'm going to find 2 nice points. Ooh, those are nice. Okay, so the slope is, I'm just gonna really estimate this, okay? I'm not in the interest of time. I don't know, what is that? 1 point, I'm just gonna call it 1.3 minus, oh gosh, what's that? Point, oh, I'm just gonna say 0.1. Oh, wow, I really got excited about that decimal point. Okay, divided by 5.8 times 10 to the minus 3 minus 0.4 times 10 to the minus 3. And if you calculate, earlier I calculated a slope of, well, it's supposed to be 217, but I don't know what that, meters squared per kilograms second squared. And then if you solve for C, you'll get 0.045 kilogram per meter. Okay. Sorry, that got cut off over there. I'll rewrite this for you smaller. I have to pay more attention to that. Mg over C. Now you can see it. Y equals mx, and our x variable is the mass. Right there. Can you see it? Okay, sorry about that, guys. I'll try to pay more attention. All right, let's remember our value for C, 0.045. We'll put it on the next screen. Okay, try that. Hi. Okay. I think what we need is a force diagram. Gosh, they're so helpful. Okay, so we have force of the earth on the coffee filters, and then it's small, right? Force of air on coffee filters. But as time goes on, what happens? The force of the air gets bigger. Of course, the force of the earth is constant. The magnitude is just mg, so it's just the same. But the air resistance force gets bigger and bigger. So what's happening to the acceleration? At first, the acceleration is down and it's big, and that downward acceleration gets smaller and smaller and smaller until eventually when you reach terminal velocity, a is 0. Remember, acceleration is slope of velocity. You know it approaches a constant value, right? So this value, right when it reaches terminal, where is that? Maybe in this neighborhood, capital T, they told us to label, and then maybe, let's go over, that's a roughly horizontal line, V terminal. How about that? It's not a great horizontal line, is it? That's okay. All right, suppose you had a graph like the one you sketched. How could you use the graph to get the distance it traveled? The distance y. Oh, the distance y is how far okay, so the distance y would be this area, right? So you would just find the area, okay? Now, I don't know if they gave you the function or not. It just says you would have a graph. If you had a graph, you would have to count the squares. Otherwise, if you had the function, you could integrate. Okay, determine expression for the amount of mechanical energy dissipated. So what did we say at the beginning today? We said work done by a non-conservative force, and this is a dissipative force, so it's non-conservative. That would be the change in potential plus the change in kinetic. So as these coffee filters fall, they lose gravitational potential. So I guess they lost mg y, so distance y, and it gains kinetic energy. So that's the work done by non-conservative forces. Okay, it lost gravitational potential and it gained kinetic. Okay, this one should be quick. Try this. Okay, so it says negligible friction, and it starts from rest. So V equals 0 at x equals 0. Okay, so what does that mean? That means at x equals 0, it's all potential energy. So kinetic energy is 0, right? So that means if there's negligible friction, then there are no dissipative forces acting. So there's no, if it's the object Earth system, then the total energy should remain the same, which is almost at 14, right? So this blue graph is the total mechanical energy, which means the graph of the kinetic energy would look like that ish. So this is the kinetic energy. And it's asking where the maximum velocity is. The maximum velocity is where the maximum kinetic energy is, and that is at 3 meters. Okay, try this one. Okay, so force is negative du dx. I did the graph for you. I think you guys can all get that. So we're going to take the negative, the derivative of this function 4 over 2 plus x. So it would be 4 times 2 plus x to the minus 2, right? So the original function u of x is 4 times 2 plus x to the minus 1. So take the minus 1 out front and then take 1 away from the exponent. Okay, so there's your force equation. Suppose the object is released from rest at the origin. So v equals 0 at the origin. Determine the speed at 2 meters. So if it's released from rest at the origin, that means the total mechanical energy is 2 joules because there's no kinetic energy at the origin. It's all potential, and the value of the potential energy is 2 joules. Okay, so the speed at 2 meters, at 2 meters, it has 1 joule of potential. So 1 joule plus how much kinetic? Well, if you do the math, it'd be 1 joule, right? So you say 1/2 mv squared equals 1, and the mass is zero 0.5. So if you take half 0.5, you get a fourth. Put it on the other side. V squared is 4, so V is 2 meters per second. In the laboratory, you're given a glider of mass 5.5 kilograms, and it's acted on by that force. Find the validity of this value, 2 meters per second. So we're trying to see if it's really going 2 meters per second when the object is at a position of 2 meters. Okay, so what do we need? If we want to know, let's see. Let me just draw a little glider here. Here's my 2 meters. It's just 2 meters. I kind of want to put a photo gate there, and then my glider is going to zoom through it, and it should be able to give me the velocity, right? Oh, you know what else we need? We need a ruler or something. I'm going to draw it up on top. That's a ruler. Okay. So I'm going to get, I'll call it a meter stick and a photo gate timer. So if you measure the width of your glider or the flag on your glider, and then you put your photo gate, I think it's gate mode, then it'll measure the time that the beam is blocked. So it'll give you the velocity. So outline the procedure. So yeah, you would measure the width of the glider or the flag on the glider, and you would it's just it's magically acted upon by this force, so you don't have to do anything. It's just somehow acted on by that force, and all you want to do is measure the speed at the position of 2 meters. So yeah. Okay, this object is moving from A to B to C and then to D. Answer that question for me. Okay. If you look at the force at position C, there is a component of the force tangent to the path. So that means that it's going to do positive work, which means the kinetic energy should be increasing. Okay, let me see what's blocked here. Give this one a shot. Okay, here's our hill. It's released from rest at height h. There's no friction, and it reaches the bottom with speed v. Okay, now it's going to be released from rest from a rough hill. Here's my hill that has friction. Hope you like that. Height h. It's released from here, and it says it loses 1/2 the mechanical energy. So what I'm going to do is I'm going to draw a blue arrow to say half the mechanical energy went out of the system because there was a dissipative force acting, friction. Okay, so that means at the bottom, if the total energy of this system here is 1/2 mv squared, right? There was no friction, and it ended with an energy of 1/2 mv squared, assuming the bottom of the hill is y equals 0. That means it also had a total energy of 1/2 mv squared at the top of the hill. I'm not saying it has kinetic energy. I'm just saying the quantity, the amount of gravitational potential energy was equivalent to 1/2 mv squared. Okay, so that means the amount of energy down here it will have is 1/2. Well, it's half of half of the energy from the first situation, which is 1/2 mv squared. So this is equal to the kinetic energy of the block at the bottom of the rough hill. And I guess we'll call that speed v friction, I guess. And then if you cancel the m's and cancel one of the 1/2s, you get v final is v over square root of 2. So the velocity is smaller, obviously, but it's smaller by a factor of square root of 2. Okay, try this multiple choice. Okay, so what it's saying is it's on a smooth surface and you pull it to the right, x max, you let it go, and it goes through equilibrium with speed v, kinetic energy k. And then it comes to rest at the amplitude with the potential energy u. So there's no dissipative forces acting, so the energy should be conserved. And then they put it on a rough surface and they repeat the procedure. So as the block moves to equilibrium and comes to rest, which of the following is true? Okay, so they started at x max, they let go, and they say as it moves to equilibrium, half the energy is gone, right? So if we draw this, if we pull it to x max, this distance would be x max. It starts with an energy u, and if there's no friction, it would have an energy k here, right? But since there's friction, it only ends up with half the kinetic energy because at equilibrium, it doesn't have any spring potential, right? So it would have half the kinetic energy at equilibrium as the other situation. Its speed isn't half though, right? Its speed would be 1/4. Spring constant is the same. It's the same spring. The block has the same mass. It's the same block. And then the potential energy when the block comes to rest after passing equilibrium is going to be less than half because it started off at the amplitude over here. It's going to zoom through equilibrium and lose half its energy. It's going to lose even more energy after it passes that because after it passes equilibrium because friction is going to transfer energy out of the system. It's going to continue to do that after it passes equilibrium. Okay, try to find the maximum stretch and maximum velocity for this spring object system. Okay. So you have this potential energy function over versus time of an object oscillating on a spring, right? Well, you know that when the maximum potential energy, it's not moving. So right here is the object has all spring potential energy. That means it doesn't have any kinetic. So the total mechanical energy of this system is 2 joules. And at the amplitude, that 2 joules is all spring potential. And they gave us K as 100. So 2 over 100 square rooted. Can I do that? Wait, no, that's wrong. 250. 2 over 50. Well, 2 over 100 is 1 over. Oh, I better just write it out. You see, when you try to do math in your head, it just doesn't work. Okay, so that's 1 over, now it is. See, I just wrote one step and now it's fine. So 1 over 25 is square rooted is 1/5, which is 0.2. So x equals 0.2 meters. And then the maximum velocity would occur at one of these points down here when the potential energy is 0. So the kinetic energy would be 2 joules at the max. So 1/2 mv squared equals 2. And they gave us the mass is 2. Half of 2 is 1. I can do that in my head. So v is the square root of 2, 1.414 meters per second. I guess you should round it to 1.4 for sig figs. Okay, so this is the problem that the College Board is recommending you practice, that this question is going to be similar to the experimental design question that will be on your exam. So why don't you take a moment to do the best you can on this? You should be able to type it. Okay, so this is kind of open-ended. I mean, you're just testing conservation of energy, right? So, well, okay, they do say it has to start with initial gravitational potential and end with kinetic. So, let's, there's many ways you can do it. I'm just going to draw one. So if you had a track, like an air track or any kind of dynamics track, and you put a cart on the track, and then you connected it to another object, a hanging object, I'll call this M1 and M2. If you released it from rest and allowed M1 to descend some distance h, the system, well, it would be the cart hanging object Earth system, right? It would have transferred the gravitational potential energy into kinetic, right? So it would kind of look like this: E initial equals E final. So it started off with gravitational potential. Which M? Which M? Well, M1 is the hanging object. That's the one that's going to change its gravitational potential energy, right? What I mean is the gravitational potential energy of the hanging object Earth system. You need two objects to have potential energy. Okay, where did it go? How did that energy transform? It turned into kinetic energy of what? Both objects are moving, so it'd be M1 plus M2. Okay. So that's the general scenario here. So what are we going to need to measure? By the way, this is V final, right? It's very important. That's the final velocity of the hanging object after it has descended a distance h, right? Well, we're going to need to measure the masses of these objects, the cart and the hanging object. So let's do a balance. We're going to need to measure the height that the hanging object dropped. So let's get a meter stick. And we're going to need to measure the velocity of this system, right? So maybe it's easier to measure the well, okay. I'm going to draw a meter stick because they said, I think they said here, indicate each piece of equipment you'd use. Okay, well, this one we're just going to check it, so we'll come back. We need a meter stick. We're going to need a stopwatch because in order to get the velocity, we need to do distance over time, right? We're going to think a little bit harder about that in a minute. Obviously, we will need a track, a cart to put on the track, a string to connect the objects. We need, this is an experiment, right? So in an experiment, you want to see how one variable affects another variable. So I recommend we have a set of objects of different masses, and then we can see how the velocity, the final velocity, is affected by the mass that we put on the hanging object. We need a pulley. Okay, basically we need everything. Then it says outline a procedure for performing the experiment. Include a diagram of your setup. Label the equipment in your diagram. So I'm just going to do my diagram here. So this is going to be my meter stick. Meter stick. And then you need a stopwatch. I'm going to draw it like this. I don't know how to draw a stopwatch. So it doesn't matter, does it? Because we're going to label it. You can be a terrible artist as long as you label it, right? It's not an art exam. So so you have a stopwatch and I need my balance. Draw my balance. Just label it. Balance to measure. Label the equipment diagram. Measurement and a symbol for each measurement. You got to read all of these words. A symbol. So this symbol would be M. This one would be H. This one would be delta T. Right? Those are all our measurements, I think. Okay. This is good. Now I just want to bring something up. You know how we're solving for V final? V final, probably what we're going to do is to get the average velocity, which is the distance it fell, divided by the duration of time that it took to fall, right? That's what we're going to want to do. But is that the final velocity of the hanging object when it has fallen a distance h? No, that's the average. So to get the final, you would have to double the average, right? I didn't grade this exam, but I'll bet you a lot of students missed that little I don't know that detail. Okay, so we're going to outline a procedure. So why don't I'm going to share the whiteboard and let's practice typing it out. Okay, so we will type out a procedure. What should a procedure look like? Okay, so you got to start from the beginning. So um, place a cart on a track. Uh, connect the cart to a hanging object with a string. Put the string over a pulley. Right? That's basically the setup. Hanging object implies that it's vertical. Okay. What do we want to do? Measure. Make sure you say what you're going to measure and with what. Measure the mass of the cart and hanging object with the balance. We're not just saying what we're going to measure. We're going to say what we're going to measure it with, what equipment we're using. So measure mass of the cart. I'm going to put M1 just to make sure. We don't need subscripts, right? We're going to be typing this whole exam. We don't need subscripts. M2. Can a physics teacher understand what I just wrote without subscripts? Yes, they can. Okay. Measure the mass with the balance. Okay. Release the system from rest. Measure the distance h. The hanging object descends. Measure the duration of time the hanging object took to descend h. Okay, right? That's the main thing. We measured the mass. Okay, now I'm going to say repeat 3 times. Now we're going to repeat the whole procedure 7 more times with different masses of hanging objects. How's that? Right? Is that good? If it were my students, I would want to make sure they had a factor of 10 difference between the smallest mass and the largest mass. Because if you have all your data jammed up into, let's say you did 100 grams, 101 grams, 102 grams, you're not going to get good results. So I would say to make sure there's a factor of 10 difference between the smallest and the objects and the largest. Okay, we were supposed to write a procedure. I think we did it. Right? It was just the procedure. Let's go back to the question and see what's next. Okay, give a detailed account of the calculations. Okay, calculations. All right, I need a new text box. Okay, I gotta do this fast. Okay, so I would say M2, I believe, is a hanging object, right? Was M2 the hanging object? Oh, I don't remember. Oh gosh. People are gonna yell at me if I get it wrong, so I gotta go back. Where's my diagram? It's gone. Okay, well, anyway, I'm going to call it M2 now. I hope everybody's okay with that. I can't remember what I called it. M2 equals, I got to start over. I can't erase that. I'm making a new text box. Okay, hanging object. I'll just put MH for hanging object, all right? And I'll put it in parentheses. Mass of the hanging object times GH is equal to 1/2 mv squared, right? And then V final equals twice h over t. Yeah, okay, twice h over t, and then we'll have everything, right? Okay, I think that's good. You know what we need to say? We need to be a little bit more specific. We need to say K initial equals 0. You can't just assume the reader knows you know that. And U final equals 0. You've got to come out and say that. Each of those is 2 points in the rubric. So I'll bet you a lot of kids miss that on the exam. I hope that won't be you. You've got to come out and say everything you know. You can't assume we know that you know initial kinetic energy is 0. You have to come out and say it. And the final gravitational potential energy is 0. Okay. Let me go back because we are running out of time. After your first trial, the calculations show that the energy increased. How'd that happen? Maybe your lab partner, just blame your lab partner. It's fine. Maybe they accidentally gave it a little push, right? They were distracted and they gave it a little push. On other trials, your calculations show the energy decreased. Okay, maybe, you know, in my tracks, I use them sometimes with modeling clay for momentum, and sometimes the modeling clay gets into the track. So you could say, and we noticed there was some modeling clay in there, and that exerted a dissipative force, and that took energy out of the system. Okay, you could say that. We are really out of time. So, oh, this is the rubric. You can come back and look at this yourself to see how many points everything was worth. And there's a different, my scenario isn't the only one. You could use an inclined plane. Look here, initial kinetic energy is 0. That gets 1 point. Final gravitational isn't, well, they're using a different system than we did. We would have had to say that it was 0, okay, in order to earn that point. We didn't, we have to be careful. Okay, and then they give you the rubric for the rest of it. You guys can look at this later. Here's your homework. Okay, do this one. Do this one with your teachers, with your friends. Do it at home. Okay, do it at home. That's where you're safe. That's where we're all safe. I hope you guys will stay there. I hope you guys will be very healthy. I know it's a long time to stay at home, but we can do this if we all just follow the rules. Okay, you guys take care, and I will see you next time.